Hello, my name is Miguel Castillón, and today I will present our latest work on non-rigid point cloud registration. This work is the outcome of a collaboration between the Underwater Robotics Lab at the University of Girona and the Autonomous Systems Lab at ETH Zurich. At the Underwater Robotics Lab of the University of Girona, we have recently developed a 3D laser scanner that enables us to perform accurate 3D mapping and mobile manipulation. Here, you can see the scanner mounted on the Girona 1000 AUV, while it inspects a mock-up structure of an offshore industrial site in our water tank. Our sensor allows us to scan around 50 lines per second, which amounts to around 100,000 scanned points per second with millimeter accuracy. In order to maintain high point cloud accuracy when mapping in movement, we need to account for the 6-degree of freedom motion of the robot using odometry. The noise of the inertial sensors is therefore projected onto the 3D scan, resulting in what we call motion distortion. Here you can see an example. Despite scanning straight pipes, the original distorted scan lines are wavy. Rigid registration methods like ICP output one rigid transformation to be applied to the whole scan in order to fit the model. However, this rigid approach would not remove the distortion present in the scan. With the objective of removing scan distortion, we can analyze its nature and find two main observations. First, distortion happens only between scan lines and not inside its line. Therefore, its line can be considered rigid. That's what we call inline rigidity. Second, we observe that distortion is smooth, since it creates smooth wavy patterns in the scan. This way, we can define our goal as finding the rigid transformation to be applied to its line in order to best fit the model. However, we still need to figure out how to impose smoothness in our solution so that the structural topology of the scan is maintained. In the literature of non-rigid registration methods, one of the most popular algorithms is coherent point drift, or CPD. Given 2 point clouds, one fixed and one moving, CPD's goal is to find the translation that needs to be applied to each point in the second to best fit the first. In order to maintain the spatial coherence of the moving point cloud throughout the registration process, they impose smoothness in their solution using motion coherence theory. The main premise of this theory is that each point in the moving point cloud must remain close to its original neighbors. This implies that points close in space must share similar translations. In order to formulate our method, we drew inspiration from CPD. However, we realized that the distortion in our scans comes from noisy road trajectory estimation, whose error evolves smoothly in time thanks to the navigation algorithm. Therefore, in our case, it is point near in time and not necessarily in space that experience similar deformations. As a consequence, all the points belonging to the same line will share the same rigid transformation because they were all acquired simultaneously. This implies that the dimensionality of our solution, space, will be proportional to the number of scan lines, which is 2 or 3 orders of magnitude smaller than the number of scan points. We formulate our method as a minimization problem to be solved using expectation maximization. In the maximization step, we seek the rigid transformation that we need to apply to each point in the scan in order to minimize the distance with respect to the points in the model. The weight that each error term has in the total cost function is ruled by a correspondence probability, which is iteratively computed in the step. Please note that all the points in the scan belonging to the same line share the same rigid transformation. We enforce smoothness in the set of rigid transformations via these two regularization terms. These terms penalize neighboring lines having different transformations using a Gaussian kernel G defined in the space of line indices. One of these terms relates to the translational part of the solution, while the other one refers to the rotational part. Applying our method to real data gathered experimentally with our underwater laser scanner can effectively minimize motion distortion. Here you can see the outcome of the iterative registration process. We benchmark our method against CPD using synthetic and real data. These quantitative results show that our method consistently outperforms CPD, except for a few outlier cases. And what is more, the inline rigidity enforced naturally by our method ensures that the shape of the registered scan is consistent. On the other hand, CPD fails at maintaining global structured coherence in the registered scan. Finally, we also compared the runtimes of both methods for different number of scan lines, points per scan line, and total points in the model. As we expected from our formulation, our method is noticeably faster than CPD because its solution space is proportional to the number of scan lines, whereas CPD scales with the total number of scan points. Thank you very much for your attention, and please do check out the open source implementation of our non-rigid registration method.